So in our previous discussions in, say, a General Chemistry 1 course of thermochemistry, we spent quite a bit of time tabulating this quantity that we called enthalpy. And we used the variable H to designate enthalpy, and differences in enthalpy between the products and reactants we called delta H, delta just being the sign for change. But enthalpy is generically simply the heat of reaction, so it's whether or not heat, energy, needs to be added to the system or released from the system by really just accounting for the energies in the bonds of the system. And so we could think about this pretty simply, that if the overall change in enthalpy is negative here, then that means there's some heat that's being released from the system that came from the breaking of these bonds. It means the breaking and the making of these bonds, the difference of those, actually released energy from the system. That implies that we are at a higher energy state than what we ended at, which in this case releases heat, and we can call this a spontaneous reaction. This is an exothermic reaction, because it is releasing heat that comes from the negative sign there, which again just simply comes from the fact that we're starting at a higher energy and ending at a lower energy, and we're calling this spontaneous. But it's important to know, and I'm saying this is spontaneous purely from observation. I'm not saying that because of delta H. I'm saying this is the combustion of methane. This is natural gas and oxygen to make CO2 and water. This is a spontaneous reaction, I'm telling you that. But it's important to note that exothermic reactions, those that have negative delta H, do not necessarily have to be spontaneous. And this is where we need to understand a little bit more nuance, in that the change in enthalpy is not the only energetic quantity that is changing when a reaction occurs, and we actually need to account for both the enthalpy and this other thing that we call entropy to understand the overall energy change of the system. A couple pretty intuitive examples of this are water in ice form. And the fact that if you leave that out at something that's warmer than freezing, it's going to spontaneously melt. So we're taking water in the form of a solid, and it's being converted to a liquid. Energy from the universe has to drive this process, right? Some heat has to go in to break those hydrogen bonds that are holding it in the crystal lattice to make it liquid. That heat is coming from the room, in that case, which is part of the universe. But in that case, that means that's a positive delta H, meaning heat is coming into the system, but it's still a spontaneous process. So how is that possible? Similarly, if you have a cup of water and you leave it out for a couple days on your countertop, heat from the room is also going to cause that stuff to evaporate and make some gas. Again, that takes heat from the universe, positive delta H, but it's a spontaneous process. And this is because of entropy. And so it's enthalpy, which is the heat either being added or released from the system, and entropy, that together, both of these things are just different types of energy. They're both energy, but both different types of energy, and we need to take them together to understand the overall energy change, which helps us understand whether a system's spontaneous or not. In the end, the criteria is still the same. We need the overall energy of the system to decrease for something to be spontaneous. But that doesn't mean that enthalpy has to also decrease. That's the sort of misnomer here. So enthalpy, like in the cases of water here, enthalpy can actually be increasing, can be going uphill. But somehow balancing that with entropy, that means that overall the energy is still decreasing in the system, which allows it to be spontaneous. So how does that work? So just to be clear, entropy is a really complicated idea, and we're going to oversimplify it quite a bit in this class because it's so complicated. But I think we can generally consider entropy as molecular randomness or disorder. So anything that is more random or more disordered after a change means the entropy of that thing has increased. So the universe is always striving towards more randomness. Order is the antithesis of the universe. The universe doesn't like things to be in perfect places and positions. It always is striving for things being more random. And in these two examples, that might make some sense because in this first example where you have a chunk of solid ice, that means water is actually locked up in this perfect crystal lattice. So a little snow crystal has water oriented in perfect spots, perfectly ordered. And then in liquid water, we know that the water is still kind of bound to each other, but it's not perfectly ordered anymore. There's freedom for it to move. So there's more disorder here, which we use S for entropy. And so we can say that this system had a positive change in entropy because it went from highly ordered, perfectly ordered crystal to something that's more disordered. And the same can be true for the liquid state. So we're going from something that has not a ton of long-range order, but they're still in contact with each other in a liquid form, to a gas where those molecules are actually no longer even interacting with each other. They're mixing with the environment, which means, again, a much higher entropy or state of disorder. And so gases are always going to be more disordered than any crystalline solid. Another intuitive example of how entropy can change in a system by just looking at a chemical reaction is something like this, where you have N2O4 that literally splits apart into two NO2 molecules. Which of these has more order? Well, in this case, you have 6 atoms, and we don't need to draw them out, but let's just say that there's 6 atoms, and they're all perfectly arranged to each other because they're covalently bound to each other. And then you have a system where you have 6 atoms, but now they're in these clusters of 3, where those things can be quite a bit further away from each other, right? There's nothing that says they have to be in contact. And so the order for the system is much higher as a reactant because we're going from one thing to 2 things. And so in this direction, we have increasing entropy. Simply because we are allowing the system to exist in more states than it would if all 6 of those atoms were bound to the same molecule. Dissolving salts oftentimes, not always, but oftentimes results in an increase in entropy for a system, and that's sort of by similar logic, where for like a grain of table salt, you have sodium ions in direct contact with chloride ions in this perfect cubic lattice that extends infinitely through that solid in 3 dimensions. And so once you liberate those and allow them to now be surrounded by that hydration sphere that we know exists, which actually allows this to dissolve, then the overall randomness is increasing when we dissolve this thing. I say this is generally true for most simple ionic salts like this, but it's not always true. And the reason it's not always true is because this is also an ordering process. Anytime you're forming a hydration sphere around these ions in solution, you are putting them in a position that is not random. And specifically for something like sodium, it turns out that there's about 6 of these water molecules that form sort of like this hexagonal structure. It's a transient structure, but it's still there, which means that it's less disordered than if it were perfectly random water molecules sort of bouncing off. And so for some systems, something like calcium sulfate, for example, actually has a negative entropy when it dissolves because it's actually more ordered when it's dissolved than it was in the crystal to start with.